Hi, I'm Keith Johnson from Lab M08. This is too loud. Hi, I'm Keith Johnson from Lab M08, and for my last lab, I'll be modeling the solar system. In the solar system, the only real forces acting are gravity, and the force of gravity is equal to gmm over r squared, where the masses are the mass of the sun and the mass of whatever celestial body we're looking at. So the system, F net, goes directly towards the sun here, and the velocity of the planet is perpendicular to this. The solar system data was retrieved from this website. The distances from the sun were taken from here, and the orbital speeds from here, as well as the masses in relation to Earth. Using this data, we were able to update the position by going via the momentum. The momentum was updated because it's equal, dp dt is equal to F net. With this, we were able to find the momentum, which we then divided by the mass and adds a velocity to find the new velocity. This new velocity was then multiplied by time and added position to get our new position, r. When we have all this plugged in, with all our masses and initial velocities, we can run this in Python and model our solar system. So here we have all our planets orbiting. Depending on how long we run them, we can see more of the orbits. Neptune and Pluto are not currently on screen, but they eventually come around here. They're just a little slower because they have longer orbits, but we'll see them later. Now to see this as an accurate model, we ran it a specific amount of times and see if it matched up with what we expected. To do this, we looked at the period of evolution here, and then ran my program in amounts of time equal to what one orbit should be. So for instance, if you run it for 0.241 years, the time it takes Mercury to orbit, we see we get this one white circle, which is the trail of Mercury, making one orbit. If we run it for 1 year, Earth's orbit is just completed one revolution. If we run it for 11.9 years, the time of Jupiter's orbit, we get an almost complete circle. There's a tiny bit of discrepancy right at the top there, but it's fairly close, showing that it's a very accurate model. And then finally here we have Uranus's, the last one that fits on the screen, and it also only has a small discrepancy near the end, so its orbit is almost exactly right, which, considering the fact that the orbits of these planets are not exactly circular in real life, means that this is a very good approximation for what it represents. The orbits here of Neptune and Pluto can finally be seen. So just for fun, we have a what-if question. What if being, what if gravity were stronger? So to find this out, we change our gravitational constant from to the negative 11th to negative 10th. And we see Mercury shoot off there, and then Venus taking a very erratic plot in there, and then the rest of the planets assuming large elliptical orbits. Now we didn't change any of the masses or initial velocities, and this is what results. It's an interesting look into what would happen if physics spontaneously changed. Well, thanks for watching my final lab of the semester, and enjoy your year. Bye. Like, that was unintentional.